So let's consider using output control in order to improve the performance of a system and analyze it using root locus. So the simplest kind of control would be maybe some kind of feed-forward control on the system. So we've got a plant, which is something we want to control. An input going to that plant is going to be, if you like, the control input that's getting it to do what we want to do. And the question is, how can we improve that motor command? And what we can do if we want to is we could put effectively an inverse model in front of it. So rather than feed the goal directly into the plant, what we do is we feed the goal into an inverse model, which then converts it, if you like, into the suitable representation to get the plant to do what we want it to do. However, I'm not going to go into all the details of inverse models here. I just want to point out that this is a particularly simple arrangement. Inverse model could be as simple as a gain. It could be just we're scaling the value up in order to get the plant to the value that it's actually we want it to do. But the point about this is that this is a completely feed-forward system. So we're feeding in the input goal here, and we're feeding all the way through, we're getting an output, but we're not looking at what the output is, and we're not doing something with the output to improve the input or at all, anything like that. This is a simple feed-forward problem. Now, the advantage of doing it feed-forward is there's no danger of it going unstable. We're not measuring the output, feeding it back in and generating positive feedback by accident. That can't happen. But this system's only going to work if the plant, first of all, is known and we know what to do with it, and secondly, if there's no disturbances in the system as well. But if that's not the case, then we can have problems. And because of that, quite often we'll look at doing something using the feedback of the system. Now, it could be that we're building an amplifier, or it could be building a robotic arm, and we've got a goal that we want the thing to go to. It could be an arm and you want it to go to a certain position. And generally what we want to do is, first of all, process the information slightly so it's in the right kind of form to control the system that we're controlling. But then what we do, we don't just assume it does what we want it to do. We actually measure what it's doing and look at its output and feed this measurement back to the input, and then compare it with what we've actually wanted it to do, and we generate this different signal, and it's the different signal that actually drives the system. And in this way we can actually get systems to perform much better than just assuming that we can just tell it what to do and hope it does what it does. But using this particular example, we're just using the output of the system. We're not doing anything more sophisticated. We'll talk about that when we talk about state space models. But the point is, this is a closed loop system. It's looking at the actual output and we're feeding it back to the input. Now, the problem with this is feeding the output back to the input can lead to the system going unstable, right? So if we feed the output back and normally we're taking it away, if for some reason there's a phase shift or and the gain is high enough, we'll actually be feeding something back which is positive, and we'll end up with positive feedback and the whole system will go unstable. So this is where, as a simple way of analysing output control strategies, the concept of root locus comes in useful. And what we're going to think about, let's just think about this simple arrangement. We're going to say we've got some kind of controller C of S, we've got some kind of plant G of S, and we're going to feed things back via this feedback path H of S. Now, generally we'll need to design a controller C of S so this works better. But let's just call it C of S at the moment, and we'll worry about that later when we come to other controllers. Now, if we're designing this system, what we need to do is design it such that when we do this feedback, we end up with a system which is stable, which means the poles need to be appropriate located in the S domain. So in a nutshell, we need that the real part of the poles are negative. Now we can simplify this diagram quite easily using a couple of, if you like, simplification rules. We know that two things in series just multiply together, and we know that a feedback system can also be simplified. So we can quickly simplify this as the system corresponding to the following transfer function. So the feed forward part will be CSGS, so that the overall transfer function with the feedback loop is going to be CSGS divided by 1 plus CSGS times HS, because HS is the feedback path. Now we can look at this equation and we can immediately say when the poles are going to occur, because we can see that this then corresponds to the denominator term going to 0, right? So when 1 plus CSGS HS goes to 0, we know we've got poles. So in other words, when the denominator goes to 0, this is called the characteristic equation. When that goes to 0, we find the poles. So let's just remember what the S domain and stability look like. First of all, if we've got negative real parts to the poles, that's all of this area here, everything to the left of the imaginary axis through 0, we have a system which is going to be stable, right? And if we've got positive real parts, it's all going to be unstable, right? If we've just got poles which are lined along the real axis and they've got no imaginary components, then there's no oscillation happening at all, right? So if we've got a value which is bang on the origin, no real component at all, and also no imaginary, then we have a system which is going to be constant and not oscillating. But if we've got a positive part here in the real part and no imaginary part, we're going to have an exponential increase, and conversely a negative real part only, we've got exponential decay. And as you start adding in complex things, you get the same effect, but this becomes the envelope of some oscillation. Okay. You can also say a lot about what the system is doing by looking at this as well. It could be that you want things to settle really fast, in which case you want bigger values in the negative real part, so that the decay is really quick, depending on the requirements of your system. So the idea of root locus now is going to be that we can actually work out where the poles of the system is going to be in a feedback system as a function of the forward gain in the system. So as we change the gain, we change the location of the poles, and we'll be able to see by plotting where the poles are and what their trajectories look like as a function of the gain, what the system's going to be doing. And generally speaking, we can say, yes, we want the poles never to have a positive real part, and we want them to be in such a location that we're meeting requirements such as settle time or critical damping or something like that. So let's think about some very, very simple sketching rules. We don't need really to care at all about sketching rules apart from maybe these two issues, because 100 years ago, well, I don't know if it was 100 years ago, but it was a long time ago, people obviously had to do this because they didn't have Matlab or computers, so you had to do things by hand, and they would sketch these things by hand in order to work out and characterize circuits. We don't need to do that these days, so that's why we're not going into that in this course. So imagine we've got this closed loop transfer function, right? This is basically the depiction of what this signal flow graph looks like. We've got the forward path G, and we've got a feedback path K, so the overall closed loop response is going to be G divided by 1 plus KG. Now, we're going to get poles when the bottom bit goes to 0, right? The numerator goes to 0, so when 1 plus KG equals 0, we get a pole, right? Let's split this up, right? Let's split this term up now for the G of S, because G of S is generally going to be a transfer function, so it's going to have a numerator and a denominator, not to be confused by the numerator and the denominator here. We're just talking about G of S. Let's split this up and write when poles occur in terms of this expansion of G of S. So we now say when 1 plus K ns divided by ds equals 0, then we get a pole. And we can rewrite this. We can multiply both sides by d of s, right? Because we can do it we like. It's an equation. Then we see that d of s plus k n of s equals 0. And again, this will then hold for some real values of k. So what we can say is, looking at this expression, when k equals 0, so when the feedback gain is 0, we have poles when d of s equals 0. So in other words, and it's not that surprising when you think about it, the closed loop system poles are the poles of basically of g of s when the gain is 0. That's not surprising, because when the gain is 0, it disappears, right? This bit all disappears. So first of all, the poles of the closed loop system, it just behaves like an open loop system basically when the gain is 0. That's what it's saying. So the poles of g of s give us the poles of the system when the gain is 0. No great surprise there, really. However, let's now think about this expression again that we've got for when poles occur. And this time we're going to divide through by k, right? So we've now got this expression, 1 divided by k plus ns over ds equals 0. Now when k goes to infinity, right? So when the gain in our system goes to infinity, the 1 over k term disappears, right? So then we've got n of s divided by d of s equals 0, and we can see that is satisfied when the numerator goes to 0, right? So the numerator, and that basically is the 0 of the d of s, right? So that's maybe not quite so obvious, but what it's saying is, as the gain goes to infinity, then we end up at a point where we have the open loop 0 representing the pole of the closed loop system. Right. So let's have a think about. I mean, and those are, it's quite nice to have those. Those are two extremes that you can find very easily. Let's consider a real example now with an open loop transfer function. This is something with a nice little numerator and a bit more on the bottom for the denominator. We can use Matlab, generally speaking, and that's what we do in order to do these things, to generate our root locus, and we'll get something which looks something like this, right? So it's plotting basically where things start and then off they go as the gain changes. So the important thing is we can identify locations on this S-plane that we want to be in, and then read the gain off that we get from them. First of all, what we can see is, again, like I said, when the gain is 0, we end up with the poles being the poles of the feedforward function. So it's going to be when s is 0, when s that's there, when s is -5, that's there, when s is -15, that's there, and when s is -20, that's there. And as the gain changes, these things start moving, right? The gain things, the trajectories move. So they're moving in and then going up, and then moving in and going down, moving in and going up. So as the gain then changes, it changes the location of the poles. That's just the location of the poles when the gain is 0. So why is that useful? Well, what it means is you can think about maybe what the gain, or you can look at a system that you're designing. It could be that we're doing a PID controller, so we're sticking a controller in front of the plant, and we want to know, let's say, if it's stable or not. We can do a root locus analysis and then say, what's it going to be when the gain of the whole thing is, imagine we've got one gain in front of all of this. We can look at the root locus of this system. So what we do is first of all we get our PID transfer function. In this case, I'm just going to use an example of an inverted pendulum transfer function. Product of these two things give us our feed forward path, right? So it's going to be this transfer function multiplied by this transfer function. So that's this bit multiplied by this bit, giving us our CPPS. We need to stick in certain gains. But then what we can do is we can then, let's say we're going to put in unity gains on the PID, and let's do a root locus of the whole thing. And what it does in Matlab for you is it plots something out like this. And what it's showing you is there are regions now, right, where, as you can see, things are crossing the imaginary axis. So there's a gain here when it ends up with something which is going to be unstable. So you can look at this and see that it starts. Well, it starts off basically being unstable, but when you get a gain of an overall gain of 10 in front of it, then it crosses over the axis. So when the gain is a 10.5 or something like that in front of your PID controller, then the system ends up becoming a stable system. And we can also see from this, when the gain actually goes up to 13, it moves as far as it can along the real axis before it starts going off up and down the imaginary axis, which basically means on this particular system, a gain of more than 13, it will be stable, but it will start oscillating a bit as well. So if this is an inverted pendulum, you're giving it a knock. If the gain is less than about 10.5, it won't balance it. If the gain is 13, it will balance it, and it won't oscillate. But as you put the gain up a bit more, it will balance it, but it will start wobbling. Okay, that's all that's telling you.